And so we've come to the end of lesson 4.07, where we want to be able to find the lengths of arcs in the area of sectors. So let's look at these two things. There are a couple of things we know about a circle. One of the things we know is the circumference is 2 pi r. Okay? That's the whole circumference of the circle. If you know the radius, multiply the radius by 2 pi, and you get the circumference. Now notice, what does 2 pi refer to? 2 pi refers to the length in radians, or the size of the angle of one complete revolution of a circle. Pretty cool, right? Now we can end up getting kind of the same sort of idea when we look at a circle for area. Area is equal to pi r squared. Now, we could think of pi as being 2 pi times r squared over 2, like that. So the 2 pi is the angle around the whole circle. And so that then begins to make us wonder, what would the length of just a small arc be, any small arc, okay? Now, we know some special angles, and what would be the area of any essentially slice of pie? So this is called an arc when you have some part of the circle, and that arc corresponds to the angle. Now, one of the things we know is that from geometry is that central angles and their cutoff arc have the same measurement. So if this angle was pi over 4, then the arc would be pi over 4 as well. All right? But there was an issue with that. If you'll remember, back in the earlier days, we would have to take into account the radius, because the arc is measured in radians, but if we're going to measure the length, we have to multiply it by the radius. Why? Because we can have a circle of radius 1, or we can have circles of radius 2, right, etc. And so as the length changes, the arc length will change, but the radian size does not. And that's kind of the issue. And so we can think of any arc just like we thought of 2 pi as an angle. We could say, well, this arc is going to be whatever fraction of the circle that we have, whatever minute fraction that we have. And so what happens is we get that the length of an arc, or arc length, is equal to the angle in radians. So we put theta times r, the radius. And then the area of a sector follows the same issue. What we notice is that, first of all, this pie shape, we call that a sector, okay? And we know that a pie shape will have an area that is some fraction of the circle. What fraction of the circle it will be? Well, with the whole area, it was the whole circle, so we used 2 pi for the angle. So area of a sector, which I write like this, is going to equal theta times r squared over 2. All right? And so that's where these formulas come from. And at this point, you just need to use these formulas to find either an arc length or an area of a sector. So let's do a couple of quick examples of that. So here's our problem. We want to find the arc length for an angle of 70 degrees with a radius of 3 centimeters. So the first thing we need to remember is the mode of our calculator needs to be radian mode unless we can change 70 degrees to radians, okay? But gosh, I spelled calculator wrong. There we go. It could need to be in radian mode. So kind of keep this in mind if you have to multiply by radians, which we do in this problem. And so the first thing we know is that arc length is equal to theta, the angle in radians, times the radius. All right? And so in this case, 70 degrees, we want to convert that to radians. So we take pi over 180, and that'll give us 7 pi over 18. Now, you can also have that as a decimal, or you can just enter this for your angle in the problem. If you have a arc length that's out of whack, you could just put that in for the angle. So what's our arc length here? Excuse me, I had a little yawn. It's going to be 7 pi over 18 times 3 centimeters. All right? And so in this case, the 3 cancels with the 18, gives us 6. So we get that the arc length is 7 pi over 6 centimeters. Okay? Now remember, the angle is in radians, and you can convert degrees to radians, or they'll just say it's 2 radians long. The angle is 2 radians, and so you plug that in for that. Okay? In any case, that's your solution to this problem. What is the arc length? Well, it's going to be 7 pi over 6, which will have a particular measure. All right? So let's do an area now. So we pretty much do the same thing here. We want to find the area of a sector with an angle of 70 degrees and a radius of 3 centimeters. So once again, I write the problem down. I say the area of a sector is equal to theta times r squared over 2, okay? And then I know that r is 3 centimeters, that's r. And I know the 70 degrees, this is our theta, but I need to convert to radians, okay? And so once I know that, I can do that. So I take the 70, once again, I'll multiply times pi over 180, and in this case, I get 7 pi over 18. This then becomes 7 pi over 18 for the angle times 3 squared over 2. And 3 squared is 9. And 9 will cancel with 18 and leave 2. And so in this case, we get 7 pi over 4 centimeters squared because we squared the 3. So our units will be centimeters squared. In any case, this gives us the solution. All right? And so the problems are fairly simple, fairly snappy for that matter. So what are a couple of modifications on these problems? What are some modifications you might see, or you might see me put on a written test or some kind of written problem? What would that be? Well, let's look at that. So the first type of problem that's we'll call it a problem modification. So say you know these formulas, and you have these formulas in your notes, right? You have the arc length formula, which is equal to theta r, and you have the area of a sector formula, which is equal to theta times r squared over 2. So you have both of those, and they're in your notes, and you know how to use them. But then somebody comes along, and the first type of problem modification you get is what I like to call the do it backwards problem modification. So what'll happen is you will be given the area. So you're given area and one of the measurements, like the radius, okay? And then instead of asking you to find the area, they ask you to find the angle. So you're asked to find the angle, okay? And so in our case, let's say they tell me that the area is 10 and the radius is 2, okay? Then, if I'm doing this with arc length, or they told me the area, okay? So I'm going to grab the area formula, and that's going to be 10, because that's the area, is going to equal theta times 2 squared over 2. So that's 10 is going to equal 2 squared over 2 is 2 theta. So then 5 is equal to theta. And so what kind of units are on this 5? That's 5 radians. So remember, you're going to get a radian answer. Now, if you want, at that point, you can convert this to degrees. So you take 5 times 180 over pi, and then that's how many degrees you would have, okay? And so you can't convert it. But in general, this is like a backwards problem. Now, they could have given you an arc length, and you could have gone ahead and solved for the angle in that case, or the radius, depending upon what the other piece of information is. So this is really just what I like to call plug and chug. Use the formula, plug things in, and then just chug out the work to find the missing piece. Plug and chug. It's a great problem modification. It happens all the time when you're given formulas. So the next problem modification is a little more sophisticated. What happens is you get defined what is called a segment of a circle. So what is a segment of a circle? What would that definition be? Well, if you remember from your high school geometry class circle chapter, a segment is if you have a sector, which we all remember is a piece of pi, and you connect these 2 points, the endpoints of the radius, then what you are left with is a triangle and what is called the segment of a sector or of a circle. All right? So we want to find what the area of a segment is. And this is a common modification problem. Well, if you look at the problem, the area of a segment is the whole sector minus the triangle. Okay? It's the sector minus the triangle. All right? And if you do that, then that's going to equal the segment. Okay? So this is how you find the area. So right away we go, oh, the area of the sector is theta times r squared over 2, right? That's the formula we just learned. So what's the area of the triangle going to be? Well, interestingly, we're going to use the area formula of a triangle that we learned at the start of this chapter. Because to find the area of this triangle, you have to draw an altitude, right, to find the height. But fortunately, this is the radius over here and here, okay? So we know the radius, we want the height, and we know, excuse me, not this angle. Well, we will know that angle. We know this angle here, but because this is an isosceles triangle, this altitude is also an angle bisector. So these two angles are equal. So whatever this central angle of the sector is, if you cut it in half, there's your angle. And if you look, this is adjacent over hypotenuse, and that's h over r equals cosine 1/2 theta. So the area of this triangle is going to be 1/2, all right, the base of the triangle, which is this chord right here. You know what? We don't know that chord. That's very interesting. Oh, but we could find it as well. So I am going to change this drawing up, okay? I'm going to change it up just a little bit. And every once in a while we have to do this. I was heading down a path. I could keep going down that path, but I think it'll make it harder. So I want to make the problem easier. Is that fair? Don't you agree you always want the problem to be easier? So here's this triangle. And instead of drawing the altitude I drew, I can draw any altitude, okay? Now what I've got is my base is the radius, and the hypotenuse of this little right triangle over here is also the radius. So again, I need to find the height, okay? So in this case, I know this angle because this is the angle they give us, right? It's the central angle. So I know that's going to be theta. And so I want the height, which is the opposite over the hypotenuse, or the opposite over the radius. And so if we take 1/2 base times height, our base is the radius times our base is the radius right here, this radius, and our height comes from the formula sine theta equals h over the radius, h over the radius. And so the radius times the sine of theta is equal to the height. And so this becomes the area of the triangle. So if you take the area of the sector minus the area of the triangle, you can find the area of the segment. So let's just do one quick problem of this. Okay. Suppose, so again, you got to pay attention to the geometry. So suppose we say that the radius of this circle is equal to 5, okay? And that our central angle, so theta, is equal to 70 degrees. Now, like always, I gotta turn into radians, okay? Turn into radians. And so we've already done this 70 degrees several times. So I'll write 7 pi over 18 is theta, okay? So now we have theta, and now we have r equals 5. So all we have to do is plug these in to what we just found. So if we take 7 pi over 18 times r squared, which is 25 over 2, okay? And if we subtract 1/2 times r, which is r squared, which is 25, times the sine of 7 pi over 18. Now, this, of course, is in radians, so that's why you got to make sure your mode's in radians. It's for this kind of problem. Well, anyway, I can punch this out and figure this out on a calculator. I can just type these in and calculate it. So I'm going to let you calculate on your own. And so by taking the area of the sector minus the area of the triangle, we get the area of a segment. So in conclusion, and so in review, we have arc length equal to theta r, area of the sector equal to theta r squared over 2. We have the backwards problems where you need to solve for theta or r. And then finally, we have the area of a segment, which is the area of a sector minus the area of a triangle. And then a little reminder here, if these are your radius and you're looking for this segment, it's okay to draw an altitude to one of the radii so you know it, and then use the other radii to help you solve for the height. Okay? So that's everything. Those are kind of all the things. I think when I read your lesson, these were the only 2 problems I saw. Okay? This is what I saw in the lesson. Were only these 2 problems. But I have a sneaking suspicion they might slip one of these or one of these on you in the quiz. So that would just be my guess. That's why I kind of talked about those as well. Alrighty, that's all I have for you today. Good luck, and we'll see you in class this week. Bye.